Hello, my name is Abeku, and along with Eliza, Denny, Kusai, and Guillermo, we will be going over and explaining the shaping process for plastics. Plastics play a huge role in modern manufacturing, especially in things like packaging, automotives, medical devices, electronics, and many others. But before these materials take their final form, they go through a variety of shaping and molding techniques that ultimately can determine their strength, flexibility, and quality. When preparing a polymer for shaping, heating turns the solid polymer grains into a molten form where the polymer chains are able to freely slide past one another. This, coupled with high pressure, lets the molten grains merge together. More specifically, due to polymers having high viscosity in their melted state, shear stress is applied to the polymer while it's being worked. This means that in order to move polymer fluids through small channels or dies, high pressures are required. One of the more important properties of polymers while being worked is viscoelasticity. Viscoelasticity defines a material that shows both viscous and elastic characteristics while going through deformation. Die swell is an example of viscoelasticity occurring, which is when plastic expands when hitting the die opening at high temperatures. This occurs because the compressive forces as the plastics go through the die don't hold, and the material attempts to return to its original cross-sectional area. However, having a longer channel reduces the amount of swell.
So the extrusion process is commonly used, and it's basically when a molten polymer is pushed through a shaping die to extrude a specific shape. These can be split into a single screw or a twin screw. Single screw is the most common type for general polymer processing, and twin screw can be split again into two types of intermeshing and non-intermeshing. Intermeshing is basically where the screws overlap and the materials mix more efficiently, and non-intermeshing, the screws rotate separately with less mixing. It's found that fully intermeshing, counter-rotating twin screws have the best pumping abilities. Sheets and films are extruded by being pushed through a flat die. So the shape of the die determines the shape of what's going to come out, and to extrude a sheet or a film, it needs to be flat. And they're typically used for protective coating, flexible packaging because they're thinner, and sheets are thicker, so they're more used for thermoforming and structural applications. Multi-layer sheets and films can be made through co-extrusion, where they basically layer different polymers to create different materials. Fiber and filament production is basically where hot plastic is dumped into a heating unit, and there's three methods for this: melt spinning, dry spinning, and wet spinning. And then coating is when a layer of polymer is placed onto a material. So there's three main categories for this: wire and cable coating, planar coating, and contour coating. Wire and cable coating, the polymer is just directly applied to the wire, and this is used to protect the wire. Planar coating, there's two methods: the roll method, Dr. Blade method, and then contour coating also has two methods as well, of dipping and spraying.
Moving on past from extrusion-based molds, we're going to be talking about injection molding. Now, the main process of injection molding is pretty simple. First, plastic beads are placed into a hopper or just a location where the beads can be placed, and the plastic is heated and led into the nozzle by a reciprocating screw. Once it reaches the end of the nozzle, the screw is placing a high pressure force onto the melted plastic and is inserting it into the mold. After the solidification process happens, the clamping system on the mold is separated into two, and you can get the contents of the mold out of there. As it mentions, there are multiple variations. As you can see, there's one where the reciprocating screw pushes the mold through and melts it, and it leads into a different tunnel where there's a plunger that finishes off the injection process and applies that high pressure force through the nozzle instead of the screw itself. There's one that is just purely based on the plunger and not really using any type of reciprocating screw. Now, the advantages and disadvantages of injection molding include the fast process to actually manufacture the parts and is mostly intended for large-scale productions, as you could have multiple molds at a time while using an injection molding machine. It can create very intricate parts based on this system. Large molds, however, can be very expensive, especially if they are intricate. So they are mostly used for smaller, intricate parts in mass quantity. Another issue is that it's prone to a lot of defects. A short list of these defects are shrinking, short shots, flashing, weld lines, and sink marks. This is very common in the injection molding process, but there are ways to avoid it and go around it, as you'll see later on in the presentation. For now, it is just important to mention that there are a bunch of defects that can occur. Moving on to the next form of molding is compression molding and transfer molding. They kind of work very similarly to each other, but there are some key differences. Starting off with compression molding, the mold is separated into two different pieces, and the molten plastic is placed onto the bottom section of the mold. Then the top half of the mold is placed onto the bottom half with a lot of force and makes the molten plastic shape into the die cavity shape. And then once the process is done and cooled down, they just remove the top half and the part can be ejected. This process is more intended for simple shaped parts that need to be produced at an inexpensive rate, as this process is very cost effective, produces low waste, and also applies not a lot of stress onto the parts themselves. On the other hand, compression molding is not that good at creating intricate parts and also has a very low cycle rate compared to injection molding, which in turn just means that the production rate for these parts is a lot slower. Now going to transfer molding, the process is very similar. However, instead of having the die cavity on the top half of the bottom mold, the die cavity is actually located below. And as the top half of the mold is pressed into the bottom half, the molten plastic is shot through a nozzle and fills in a mold down below, which then can be removed from the bottom half and easily extracted. Transfer molding allows for more complex designs compared to compression molding. However, they're not as complex as injection molding. With this process, there's a lot more material waste in comparison to compression molding, as well as the ability to add other material inserts into the mold before it's actually produced. So you could have a ceramic or metal insert inside of the die cavity and then make the part with transfer molding, compared to compression molding where that is not plausible. Moving on to the next type of molding, which is blow molding. There's two main methods of this procedure. One is extrusion blow molding and one is injection blow molding. For extrusion blow molding, molten plastic is coming out from a tube and is placed in between two pieces of a die cavity that are opened. Once the molten plastic is in position, the mold is closed and pinches off the end of the molten plastic. Once that is done, compressed air is blown through the mold and allows the molten plastic to expand within inside of the die cavity and makes the shape that is intended to be. This is mostly meant for high production of plastics like water bottles and other types of materials like that, and is also very useful for larger molds. Now compared to injection blow molding, first there is an injection mold where plastic is placed into and is formed around the blowing stick. Once that is done, the injection mold is removed and the blow mold is then put in place and put around the blowing stick. Once that is done, air is blown in the same way it is for extrusion blow molding, and it spreads around the die cavity. This has higher production rates, a lot of tight tolerances, and less wasted material in comparison to extrusion blow molding, but it is expensive to produce larger molds. Before going on to rotational molding, there are a few expressions relating to extrusion blow molding and injection molding that are important to go over. We'll go over injection molding first, as this is discussing the disadvantage of shrinking that can happen with injection molding. So the expression demonstrated here, it helps determine what would be the dimensions of the cavity based on the molded part dimensions as well as the shrinkage values. It is a very straightforward equation, and to get those shrinkage values there is a table that highlights how much the plastic shrinks based on what material it is. So that's where you would get that value. And of course, the molded part dimensions, that would be something you would know based on the part you want to make, and then you solve for the dimensions of the cavity. When it comes to the extrusion blow mold, the wall thickness can be determined, as this is a very important part when making any type of material like plastic bottles and other bottle type shapes. So first there's the swell ratio between the diameter of the parison and the diameter of the die, and as well as the thickness of the parison and the thickness of the die. This just tells us how much the plastic changes and transforms within the mold. And in order to determine the thickness of the mold, we can take the swelling ratio as well as the die wall thickness and the blow mold die diameter, take all of those components into one equation, and can easily solve for the wall thickness. And the image above demonstrates where you would get each of these specific dimensions. For the blow mold die diameter, that's mostly referring to the bottom of the mold. For the parison diameter, that's mostly talking about the distance between the middle part of the mold. And the die diameter is where the molten plastic enters and is usually around the cap of a bottle. Finally, we have rotational molding, which is a very simple process. Polymer powder is placed into a split mold that is then closed and then heated and spun in a 2-axis plane to coat the entire interior. While spinning, the mold is also cooled down, and once it's done, the process is stopped and it can be easily extracted from the machine. The machine is spun at slow speeds because it's not using centripetal force, but it's actually using gravity to fully coat the inside of the mold. The advantages and disadvantages of this process is it makes simple molds that are very inexpensive. However, production times are very long, which is usually solved by the multi-cavity indexing machine, which basically allows for 3 molds to be made at the same time.
Thermoforming. And thermoforming is a manufacturing process where a sheet of heated thermoplastic is deformed into a desired shape. In general, it is used to create lightweight and detailed parts that are needed in moderate quantities. Thermoforming is a secondary shaping process, and only thermoplastics can be used, not thermosetting or elastomeric polymers, because those cannot be softened by reheating. And there are 4 basic types of thermoforming: vacuum, pressure, mechanical, and drape thermoforming. Vacuum thermoforming starts with a flat sheet of plastic. The flat sheet of plastic is heated until the plastic becomes flexible. The final shape is determined by a mold placed underneath the plastic sheet. The heated sheet is transferred to the mold and a vacuum is pulled in order to pull the plastic over the mold. The part is removed once it has cooled and hardened, and the part can be used as is or processed further. Pressure thermoforming is similar to vacuum thermoforming. However, instead of using a vacuum to pull the plastic over the mold, pressure thermoforming uses pressurized air to push the sheet into the mold. And the advantages this gives pressure thermoforming is that it allows for more detailed parts to be created. Next up is mechanical thermoforming, and this is when a heated sheet is pressed between a positive and negative mold to create a part. And unlike vacuum or pressure thermoforming, there is usually no air pressure being applied. This method allows for surface details on both sides of the part, as well as better control over dimensions. And because this method requires 2 molds, it can be more costly than vacuum or pressure thermoforming. Drape thermoforming is the most rudimentary of the thermoforming processes, and this is when a sheet of plastic is heated until it becomes malleable. The final shape is determined by a mold under the plastic sheet, and once the sheet is malleable, it is simply draped over the mold. And the advantages of drape thermoforming is that it is the cheapest because it requires the least amount of tooling compared to the other thermoforming methods. However, a disadvantage of this method is that final parts do not have a lot of detail. Next up is casting, and this is a process in which liquid resin is poured into a mold of the desired shape. The process is similar to metal casting, in which liquid material is poured into a mold, and this is a cost-effective method. When the liquid solidifies, the part is ejected or broken out of the mold. Slush casting is possible, which is when a thin layer is allowed to form and liquid inside of it is poured out, leaving a hollow part on the inside. This plastic casting is good for encapsulation of electrical components, and fettling is a post-processing process that removes unwanted material from the part, and that is often done by robotics. Casting is the preferred method when creating complex shapes compared to other methods, and it can be used to create flat and desirable optical parts that other processes cannot create. And some common materials used in plastic casting are polyurethane, unsaturated polyesters, phenolics, and epoxies. And some formulas for these methods is flow velocity, which is defined by V is equal to the square root of 2 times G times H, where V is the flow velocity, G is gravitational acceleration, which is equal to 9.81 meters per second squared, and H is the length or height of the spur. The continuity law also applies here, and the formula is Q is equal to V1A1 is equal to V2A2, where Q is the volumetric flow rate, V1 is the velocity at point 1, A1 is the cross-sectional area of liquid at point 1, V2 is velocity at point 2, and A2 is the cross-sectional area of liquid at point 2. And because of the continuity law, the sprue needs to be tapered due to the inverse relationship between velocity and area. And then we can also calculate the time to fill a mold cavity, which is T is equal to V over Q, T being the mold filling time, V is the volume of the mold cavity, and Q is the volumetric flow rate. And the time that is calculated here is a minimum because this formula ignores friction and other possible resistances when filling a mold cavity.
For polymer foam processing, a polymer is basically expanded with some kind of blowing agent. This agent can be a chemical reaction or an inert gas, and it's used to blow up the polymer and give it a cellular structure within the polymer matrix. Some common polymers used are polystyrene, polypropylene, polyethylene, and PVC.
So to summarize this presentation, let's look at some diversity of molding and forming applications, starting with industrial and infrastructure applications. When we think about molding and forming, the industrial and infrastructure sectors are some of the most impactful areas of use. These processes help manufacture essential materials like fibers, coatings, pipes, and panels, all of which are crucial for modern construction and utilities. For example, extrusion is widely used to produce PVC pipes, as you can see here on the screen, for plumbing and wiring system. The advantage of these molded materials lies in their durability, corrosion resistance, and ability to be mass-produced efficiently. In infrastructure projects, these materials help reduce costs and extend product life cycles. Whether it's coatings that protect bridges or composites panels that make buildings lighter yet stronger, molding and forming technologies play a vital role in shaping the building environments. And then on to the next one, where it is the packaging application. Packaging is one of the most visible and widespread uses of molding and forming. Think about the water bottles you see. Think about the desk we're essentially working on. Every plastic bottle, food container, and protective film we encounter is a result of precision forming techniques. The main processes used in this sector include blow molding, which creates hollow containers like beverage bottles, and thermoforming, used to shape thin sheets into trays and packaging films. These methods make it possible to create lightweight, durable, and recyclable packaging materials. This is especially important today as industries aim to balance functionality and sustainability. For instance, companies are now using biodegradable films and lightweight bottles to reduce waste while maintaining protection and shelf appeal for consumers. Now on to the next will be the healthcare applications. For healthcare applications, it really depends heavily on molding and forming technologies to create safe and reliable medical components. Example includes syringes, tubes for IVs and catheters, and even prosthetic limbs. These products require extremely high precision and biocompatibility to ensure patient safety. Injection molding is often used to mass produce sterile, single-use devices like syringes again, while vacuum forming helps produce more like custom-fit prosthetics and orthotic shells. What's especially interesting is how molding enables innovation in medical design. For instance, 3D printing and molded prosthetics can now customize to match a patient's anatomy perfectly, while in the past it used to be a standard size fit that would sometimes be uncomfortable, improving both comfort and mobility for patients. Overall, molding and forming allow healthcare technology to be safe, scalable, and accessible. And then on to the final application, which will be consumer and automotive application. Forming here are essential in everyday consumer and automotive products. Think of toys, electronic device housing, and car interior components, right? Anytime you sit in the car, you look at your dashboard, anything at all, think of this. All made through processes like injection or compression molding. These methods ensure consistency, precision, and visual appeal in high volume manufacturing in the automotive industry. Molded parts contribute to lightweight designs and that improve fuel efficiency without sacrificing safety, especially in today's world. And similarly, in electronics and consumer goods, molding allows for compact and ergonomic designs, from game controllers to appliance casings. It's the balance between function, aesthetics, and manufacturability that make molding and forming technologies central to product design and innovation. And that's about it. Thank you so much for your time.